In this video here, we're going to take a look at the acceleration of an object moving on a horizontal circular path. Now, when an object moves around a horizontal circular path at constant speed, the direction of the motion is changing, right? Now, if the direction is changing, then although the speed is constant, the velocity will not be constant. And if the velocity is changing, then what that means here is the object must have an acceleration, right? Now, let's just suppose then that the object is moving on a circular path of radius r at constant speed v. We're then going to let the time taken to move from A to B here. So this is the point A, and this here is the point B. So with the time taken then to move from A to be delta t here, and the angle AOB will be delta theta. So what I've got here then is AOB, this angle, as we can see here, as we mentioned here, right, is delta theta. And the time taken then to move from A to B will be delta t. Okay. So at this point here, that is the point A then, the velocity is v along the tangent AT. That's this line here, right? So let me just shade this here in a different color. So this is the point A. And then at the point A here, as we've just mentioned, the velocity is v along this tangent here. So along this line here, AT. Okay. And at this point here then, this now being the point B, and again, I'll just do this in a different color. Let's just do it in green then. So at this point here, B, the velocity is also v. So I forgot to kind of mention it here, but the velocity is v. And same again here at the point B, but now the velocity is v along this tangent here, TB. Okay. And again, I'll just shade this here in a different color. Now, what we can also kind of do here is split the velocity at B into components, right? Or we can resolve it into components. So what we get here then is v cos delta theta parallel to AT, so parallel to AT here. And we also get v sine delta theta perpendicular to AT. So now perpendicular to AT. Okay. So let's just keep going here in a little bit more detail. So let's just keep going then, and let's just see if we can derive the relevant results ourselves. So hopefully you should be aware of this very basic fact here, that acceleration is equal to the change in velocity divided by time, right? So if we want to find the acceleration of the object at the instant when it passes the point A, what we need to consider here then is what happens to v cos delta theta minus v over delta t, and also v sine delta theta minus v over delta t, as delta t tends to 0. Now, just notice here then that these will be the components of the acceleration parallel to AT and perpendicular to AT respectively. And for a small angle, delta theta, measured in radians, what we're going to do here, by the way, is just make use of the small angle approximations all the way back from A-Level Maths, right? Hopefully you haven't forgot these. So what we've got here then is cos delta theta is approximately 1, and sine delta theta will be approximately delta theta. So therefore then, as a result here, the acceleration parallel to AT will just simply be 0, and the acceleration perpendicular to AT will be given as v times delta theta over delta t, which is equal to v times omega. And what we can do now is use this relationship here that we first saw on our video on angular speed, right? So v is equal to r times omega. So in that case then, v times omega, that's this result here. We can write that as r times omega squared, or alternatively here, we can write that as v squared over r. Okay, so basically all we've got here then is v is equal to r times omega. This result we first saw on our video on angular speed, as we just mentioned. And all we do here is we just times that by omega. So v times omega, as we just said then, we can write that as either r times omega squared or v squared over r, right? Please do make a note of this here. This is really, really important. So to summarize here then, an object moving on a circular path with constant linear speed v and constant angular speed omega has acceleration of r times omega squared, or alternatively here, v squared over r towards the center of the circle. And this is known here as a centripetal acceleration. Now, this phrase here isn't something that you do need to be aware of, but you might have a keen interest in physics, or you might be going on to study physics at university. And this here then is a phrase that you do want to be aware of if you're going to do, physics at uni, for example. But again, it isn't essential that you do know this, but we are studying further mechanics 2 here. And I don't think this phrase is beyond us, right? We are going through some challenging maths here and challenging mechanics. So I think a basic kind of definition here, or a basic name, shouldn't be too challenging. But there we go. I'm kind of waffling at this point, right? So to finish with here then, that just gives us everything that we need here for an introduction. So to finish with then, let's just work through a couple of practice questions together. So let's just get started then with question 1 here. Now for question 1 then, what we've got here is a particle of mass 250 grams that moves in a horizontal circular radius 20 centimeters at a constant speed of 2 meters per second. So for this question then, all we want to do here is just find the force towards the center of the circle that must act on the particle. Now this question here is quite straightforward, right? Because all we need to do here is just find the acceleration. Once we find the acceleration, then we can just make use of Newton's second law here, right? F equals ma. So for the acceleration here, given that we're traveling around a horizontal circle, right? So we're looking at the acceleration of an object moving on a horizontal circular path. In that case, then the acceleration here, a, so therefore a is equal to v squared over r, okay? So v here is 2. So v is 2. Now, just be slightly careful with the radius here. The radius is given in centimeters. So what I need to do here is convert that to meters. So r then is equal to 0.2, not 20. So just be very, very careful for that. Okay. So v squared over r then, nice and straightforward, right? We get 2 squared. So 2 squared over r, which is 0.2. That's just the same as dividing by a fifth, right? So 0.2 there, or 1 over 5, whichever you prefer. So 2 squared is 4. So we get 4 over 0.2. So this is just the same here then as 4 times 5 over 1. So I get 20. So the acceleration here then is 20. So we now make use of Newton's second law here. So this is 20 meters per second squared. So using Newton's second law here, so using F equals ma, what do we get here then? So the force F, so therefore F is equal to, so the mass here is 0.25, right? It's given in grams, so the mass then is 0.25. Again, just be slightly careful for that. So 0.25 times by the acceleration, which is 20. So 0.25 times by 20, that's just the same then as 20 over 4, which gives us 5. Don't forget our units as well here. So 5 newtons there. Okay. And like you can see, then it is quite a straightforward question, but hopefully this demonstration and this explanation here has helped illustrate how we can use the acceleration of an object moving on a horizontal circular path to answer problems such as this one. Okay, so there we go. Or there we have it. That gives the solution to question 1. Let's just finish then with question 2. And then to finish with here, let's just have a go now at the very last question, question 2. Now, question 2 here is certainly more challenging than the previous question. So let's just begin by reading through the question, and then we'll take a look at this question together. So to get us started here, what we have then is a car that's traveling around a bend on a flat road. Now, the car is modeled as a particle traveling at a constant speed of v meters per second along a path which is an arc of a circle of radius r meters. We're then given that the car does not slip, and what we want to do here is find the minimum value for the coefficient of friction between the car and the road. And we need to give our answer here in terms of r and g. So, like we said, right, this question here is certainly more challenging than the previous question. Now, to begin with here, what I would do then is just draw a diagram. If you want to, you can draw 2 diagrams. And what I mean by that then is so you can either draw a diagram kind of looking down at the situation or the context of this question here. So one way to draw this would be to draw kind of like I said, looking down. So you've got a circle here. Let's just say something like this. I appreciate it's not a perfect circle, but it'll do. We've got the center of the circle here, and then we have the car just traveling along this circular path, right? So I'll put that, say, here, okay? And I'm going to model the car here as the particle, right? So what we've got here is a frictional force, right? Now the force, this force here is the frictional force, and this force is the force towards the center of the circle. And this is due to the friction between the tires of the car and the road. Okay, so that would be F there, like so. And basically, the car's just going to go around this circular path, right? But drawing it looking down like this isn't the most useful because what we need to do here is actually resolve. So what I'm going to draw here, if you think about it, it's kind of like looking at this, kind of like going round like so. Okay, so we're not looking completely down on it, but you can have the particle here. So this is the center of the circle. I've got the weight here acting downwards. So what is the mass here? So that's not given, so we'll just take that to be m, okay? So the weight then acting vertically downwards here would be mg newtons, right? So mg, like so. We've got a normal reaction here between, well, the particle, which is the car in the context of the question, but the particle here, so we've got the normal reaction between the particle and the road. So that would go up like so. So I'm just going to label that as R, right? That's just my normal reaction here. And then, like we just said before, we have this force here, which is actually the frictional force between the tires of the car and the road. Okay. We've got this here, which is F. And we also need to account for the acceleration here. Okay. So for the acceleration here, so 2 arrows here, just to indicate that this is for acceleration, then this would be, as we saw with the previous question, right, this would be v squared over r, okay? And what you can also do here is just draw essentially this diagram here from the side, which would mean I've drawn 3 diagrams, which is a little bit unnecessary, but you get what I mean, right? So we draw the particle like so. We've got the normal reaction here, that's r. We've got the weight acting vertically downwards, so that is mg. We've got this force here, F, like so. That's our frictional force. And we also have the acceleration as well, which is v squared over r. So like I said, any of these diagrams here are fine, but I wouldn't use this one. So I'm going to kind of scribble over that. It's not particularly useful in the context of this question. But that's basically what we're looking at here, okay? So it took us a few minutes just to kind of get to the diagram of the question, but it is a good habit to get into, drawing your own diagram, correctly. It's always a good starting point for any kind of mechanics problem where basically we're going to be resolving forces such as this one here. So let's just start by resolving here. So we're going to resolve vertically upwards. So resolving vertically upwards then, taking upwards as positive here. What would that give us then? So I've got r here, minus mg would be equal to 0. So in other words, r is equal to mg. Now we have no vertical acceleration, so we don't need to worry about Newton's second law here. So in that case, then r is equal to mg. Perfect. Okay. Now when we resolve horizontally here, we do have acceleration to take into account, right? V squared over r. So let's resolve then horizontally here. Given that F is acting to the left, I'm going to take to the left as positive. You can do it the other way, but I wouldn't recommend doing it like that. So let's take to the left as positive here. Like so. What do we get here then? So, like we just said, right, we do have horizontal acceleration to take into account here. So we do need to make use of Newton's second law. So what we get here then is F. Now we have no more forces acting in this direction. So what we simply get here is F is equal to ma. So I've got m, which I've took it as capital M here. So let me just kind of get rid of that so I don't cause confusion. That should be capital M. So what I've got here is capital M times by the acceleration, which is v squared over r, right? So v squared over r. Perfect. Okay. And if we just simplify this here then, what we simply get is v squared over r. Just looks a little bit neater like that, right? Perfect. So what do we do next then? Well, all we do here is we just make use of this fact here, right? That the car does not slip. So what does that tell us then? Well, if the car does not slip, just a basic property of friction here, in that case, then F is straight less than mu r, right? Let's just make a quick point of that here. So as the car does not slip, what that tells us here then is that f is strictly less than mu r, right? So what we've got here is an expression for f. We also have an expression for r. So all we need to do then is just substitute these into this inequality here, right? Now, before I do that, let me just make a quick adjustment here. So for the question, I took the radius of the circle here to be capital R. I'm just going to change that to lowercase r here. The reason being is because I took the normal reaction as capital R as well. So just to avoid any confusion here, I'll just change the radius to little r. So apologies for that. I will change it on the worksheet as well. Okay. So let's just substitute f here and r into this inequality. So f then is mv squared over r. So we've got mv squared over r is strictly less than mu times by r. So mu times by r, which is mg. Okay. So basically what we want to do here is just get mu on its own on one side of this inequality. We should be able to cancel down and just arrive at some kind of expression here in terms of just r and g, right? So what I'm going to do here then is just divide both sides by mg. Now, if mv squared over r is less than mu times mg, then we can just say here that mu times mg is strictly greater than mv squared over r, right? Like so. And like we just said then, all we're going to do here is just divide both sides by mg. That would just give us mu here on the left-hand side of this inequality. So dividing by mg then, what we get here, is mu is strictly greater than mv squared over then, so it's going to be r times by mg. We're going to get mg r there like so. Now the m's here will just cancel. So they just cancel. And what we get left with then, so to finish with here, so therefore then, mu is strictly greater than, so we get v squared. So v squared all over g times by r. Okay. And there we have it then. So this here gives us the minimum value for the coefficient of friction between the car and the road. And as we can see then, we've given the answer here in terms of r and g. Again, let's change that to lowercase r there, just to avoid any confusion. I'll do it above. There we go. Okay. So I'll just put a bubble around this, just so you can see then that this here is our solution. Perfect. Okay, good stuff. So hopefully the solution here wasn't too complicated. As you can see here, a diagram really is essential for a question like this. And it is always a good habit to get into for any kind of mechanics question where, you know, or especially when you're kind of resolving forces, it really is essential. I kind of hammered that point home in A-Level Maths. You might not have seen our videos for A-Level Maths. But I really did try and illustrate that point for A-Level Maths, that a diagram when you're resolving forces really is essential, right? And given that we're studying further mechanics too, this shouldn't really be a problem for you by now. I can't speak anymore, but it shouldn't really be a problem, right? But there we go. Okay, so there we have it then. So that gives us the solution here to the very last question, question 2. And that just brings us to the end then of this video here on acceleration of an object moving on a horizontal circular path.